Today we are going to solve the Deuteron problem. As we all know that the Deuteron is the simplest two nucleon system which consists of a neutron and a proton. So in order to determine the strength of the interaction which happens between them, that is the neutron and the proton, we solve the time dependent Schrodinger wave equation, and we assume a rectangular potential well between them, and we substitute the numerical values which we know, and then try to solve and determine the strength of the potential which is between them. So let's get started. First of all, we'll write the time independent Schrodinger wave equation, which is as follows. Here VR is the potential which is dependent only on the radial part, that is, it is independent of theta and phi, so we can call it to be spherically symmetric, and psi r is our wave function. Now we introduce the concept of reduced mass, and assuming that let us name or term the masses of the proton and the neutron to be mp and mn. So the reduced mass of the system becomes mp times mn over mp plus mn. And since we know that the masses of the proton and the neutron are comparable, that this differ from each other very slightly, so we can assume mp to be approximately equal to mn, and let us call it m. So mu becomes m square over 2m, that is m by 2. We'll be using this value later on. Now the wave function psi is a function of r, theta and phi. We use the method of separation of variables and write psi r, theta, phi to be where r is the radial part, we'll be requiring this part, and y mll is the spherical harmonics. We'll not go into much details of this, we all know how to write this, we have read this in quantum mechanics. In order to simplify the Schrodinger wave equation, we take the radial part to be of the form of ulr over r ymll, theta and phi. Now we would be using this value. Let us name the equation, this as equation 1, this as equation 2, and this as equation 3. Now we'll use equation 3 in equation 1. So our equation becomes two mu over h cut square E minus V of R minus h cut square over 2 mu L plus 1 over R square UL is equal to 0. Now since we are using a rectangular potential well, we'll define our potential well as V is equal to minus of V naught for R is less than B, and this is equal to 0 for R is greater than B, where B is the range of the interaction wherein the nucleons feel the strong force. Beyond this, the strong force becomes negligible, it does not act on it. So we all know about the kind of force which acts between two nucleons. So we can see that there are two values of v, which is negative of v naught for r is less than b and equal to 0 for r is greater than b. Let us use them in equation 4. Also, when we are talking about the bound state or the ground state of the deuteron, the value of L should be equal to 0. So we will put L is equal to 0. Why do we use L equal to 0? Because for values higher than L is equal to 0, it does not remain a ground state at all. So we'll discuss that in the later part of the discussion. So let us use these two values of the potential and write two equations corresponding to equation 4. For r is less than b, we have d2u in over dr square plus 2 mu over h cut square e plus v naught u in is equal to 0, and for r is greater than b r is greater than b, sorry, d2u out over dr square would be an equation of this form. So let us name them 5a and 5b respectively. Now we have defined two radial functions, that is u in and u out, correspondingly for r is less than b and r is greater than b respectively. And since we are talking about the bound state of the deuteron, so we will put the energy to be negative. Therefore we will use E is equal to minus of ED, since it's the bound state. So I'll highlight this for you. So wherever we are using capital E, it would be replaced by minus ED. So our equations 5a and 5b become d2u in over dr square plus capital M over h cross. We have used the value of reduced mass, that is mu is equal to m by 2 here, and our equation become as written: minus m over h cross square ed u out is equal to 0. Let us name them equation 6a and 6b respectively. Now using some substitutions, we'll try to contract our equations. So we'll put k1 square is equal to m over h cross square v naught minus ed. D is in suffix, please excuse my handwriting. Alpha square is m over h cross square ed. K naught square is m over h cross square v naught. So we can write k1 square is nothing but k naught square minus alpha square. Okay, so our equations 6a and 6b become u in double dash, wherein double dash represents the double differentiation, plus k1 square u in is equal to 0, and u out double dash negative of alpha square u out is equal to 0. Let's name these equations 7a and 7b correspondingly. Okay, so as we know, the solutions to these equations are standard, so we'll directly write the solutions. The solutions will be u in is equal to a sine k1 r plus a dash cos k1 r, and u out is equal to b exponential minus alpha r plus b dash exponential alpha r. Let's switch to my black pen again. Okay, so these are the solutions. Now we all know that u in and u out are nothing but the wave functions. So whatever conditions apply to the wave functions, that it should be finite everywhere, it should be continuous, it should be square integrable, all are applicable to u in and u out respectively. So first condition that we use is at r is equal to 0, u is also equal to 0, and as we know that r is equal to 0 will stand true only for the case where r is less than b. We cannot use it for the case of r is greater than b, since we know that psi is equal to u over r. Therefore we can write u as psi dot r. So if r tends to 0, then u will also tend to 0. When we use it in equation 8a, suppose, and 8b, using above in equation 8a, we get u in is equal to a sine k1 r. Okay, because we'll get a dash equal to 0. You can solve it and see for yourself. Also the other one, for r is greater than b, so we'll take the maximum possible limit. For the case of r is greater than b, if r tends to infinity, now we know that the wave function has to be finite everywhere, it has to be square integrable, that is integration of u square dr has to be finite. So in order for it to be finite, if r tends to infinity, then u has to tend to 0. Therefore we can write if r tends to infinity, u has to tend to 0. So using this condition in equation, let us write using above in 8b, we get u out as b exponential minus alpha r, that is only the decaying, exponentially decaying term will be sustained, the exponentially rising term will vanish. Also, if we use the other important property of the wave function, that is its derivative is continuous, so using these two properties we can write the following, that is u in dash over u in at the boundary, right? So we will write that r is equal to b, this should be equal to u dash out over u out at the boundary. So we have combined our two equations and have written this. So when we differentiate our equations, let us name these equations, we have to keep naming them. Let us name it as 9a and this as 9b. Using 9a and 9b, we have k1 cot k1b is equal to minus of alpha, or we can write cot k1b is equal to minus alpha over k1. Putting the values, we get this to be equal to minus of ed over v naught minus ed. Okay, so this is our equation which we have got solving this. So for a just bound system, we can put ED to be equal to 0. So for a just bound system, put ED equal to 0. If we put ED equal to 0, this implies that alpha is equal to 0 and K1 is equal to K0. So then we can write cot K1B is equal to 0, or you can write K, or we can use, like, we can write this to be K0, which would be more simplified. Cot K0B, or K0B would be equal to then pi by 2. So we know that the value of K0 now becomes, K0 would be M VO over H cross square. And now since we are using this for the just bound system, we are calculating this value for the just bound system, so we will replace VO by VOM, that is the minimum value of the potential required for the just bound system. So minimum depth of the potential. So this value has to be M times V naught M over H cross square times B is equal to pi by 2, or we can write V naught M times B square is nothing but pi square H cross square over 4M. This is a constant, so we can write that VOM times B square is a constant quantity, right? And we could substitute the values of pi square H cross square and the value of M, which is the mass of the neutron or the proton, and calculating it, we get VOM to be equal to 25 MeV, wherein we have used B to be equal to 2 femtometers. Okay, so we have already calculated this equation, which is cot K1B is equal to negative alpha, K1 cot K1B is equal to minus of alpha. Now if we multiply this equation, both LHS and RHS with B, we get the following equation, and we also rearrange the terms. Cot K1B is equal to minus alpha B over K1B. Okay, so we can put K1B to be equal to X, and we can write this equation as NY is equal to cot X, so we can get an equation in X and Y. So this is a diagram which I have tried to draw, which represents this, wherein Y is equal to cot X and X is equal to K1B, or we could write Y is equal to minus alpha B over X. So first of all, we would draw the diagram of Y is equal to cot X, and then we would draw the graph for Y is equal to minus alpha B over X, and we would see the points wherein both the curves are intersecting each other, and we can see that they intersect at the odd multiples of pi with slightly greater values. So we can write it to be that the value of X, which is K1B, so therefore K1B becomes greater than equal to 2n plus 1 pi by 2. As we can see from this diagram, it is clear that the values are slightly greater than pi by 2, 3 pi by 2, and so on. So we have used this value, or we could write that K1B is equal to pi by 2 plus epsilon naught, because we are making calculations for the ground state, so we'll take n is equal to 1. Here we can write n is equal to 0, 1, 2, 3. Sorry, we'll take n is equal to 0, so we can write k1b is equal to pi by 2 plus epsilon naught, where epsilon naught is a very small number. Or we could write it this way, or we can, taking cot both sides, cot of k1b would be equal to cot of pi by 2 plus epsilon naught, which is equal to minus tan epsilon naught. And since epsilon naught is a small value, we could write it to be minus of epsilon naught, right? So then the value of k1b times cot k1b becomes minus of pi by 2 plus epsilon naught times epsilon naught, and this value has to be equal to minus of alpha b, right? So on solving it, putting the values, we know the value of alpha, we know the value of b. When we solve it and expand this equation, we will get something like this, which is minus pi by 2 times epsilon naught minus epsilon naught whole square, which is equal to minus alpha times b. And since alpha naught is very small, epsilon naught is very small, we'll neglect it and put epsilon naught square is equal to 0. And using this equation, we'll get 2 alpha b over pi, and its value comes out to be 0.295. Therefore k1 b becomes pi by 2 plus epsilon naught, its value becomes 1.87. Also, since b is equal to 2 femtometers, and we know that k1 is equal to m over h cross times v naught minus ed, we have already calculated the value of k1b, which is equal to 1.87. We know the value of b, we can calculate the value of k1, and we already know the value of m, we know the value of h cross, and so our only aim is to find out the value of v naught. And what is ed? Ed is the binding energy of the deuteron, and in this case ed is nothing but 2.226 MeV, which we already know, which is a calculated value. Therefore, solving this, we get V naught minus ED is equal to 36 MeV, or we can say V naught is approximately equal to 38 MeV. So this is the depth of the potential well, which we have considered in our case. So that's all for today's video. We'll see you in the next one, and we'll discuss more about this and the subsequent applications of this problem. Thank you.